Hi everyone, this video is about directional derivatives. So we've seen partial derivatives before. That is, if we've got some function z equals some function of x and y, then if we pick a point on the surface that describes, then the partial derivatives tell us how the height of the function changes in directions parallel to the coordinate axes. So I can see how the function changes if I'm running parallel to the x-axis or parallel to the y-axis. But of course, those aren't the only options. We could move in any infinite number of directions from some point on that surface. And it'd be nice if we could figure out how the function is changing if we go in some particular direction. So what we want to do is generalize partial derivatives and get something that's not just coordinate axis specific. What that's called, if we want to figure out how f is changing in the direction of some unit vector, say in the xy plane, is the directional derivative. And here are a few different notations for that. There's the partial symbol, or the capital D, or this other strange looking sort of upside down delta that we'll talk about in a little while. So what we're looking for is the directional derivative. How would we figure out what this thing is? Well, if we look straight down on the xy plane, and we pick out some particular point, so above this or below the xy plane maybe, is where the surface is, and from this point what I want to do is move in some direction. So if I've got some vector in the xy plane, one way to describe what direction we're moving in is to give the angle off of the positive x-axis. And if we imagine that going from that point, say x naught, y naught, to some other point, x naught plus some parameter h times cosine of theta, and y naught plus that same parameter h times the sine of theta, we'll see that what that's doing is moving us in the direction of this vector, unit vector, cosine theta, sine theta. So make sure first that you see that this vector v is a unit vector, and then make sure you see by the trig that that's the correct coordinates for some point after we've moved some distance along the direction of that vector from our starting point x naught, y naught. So then what we can do is define the directional derivative in the direction of v in this way, with just limit definition of the derivative, where what we're doing is shrinking that parameter down to 0, and of course, no matter what the value of the parameter is, it's always still the direction of that vector v, and so we just shrink that value, look at the limit as the parameter goes down to 0, and that'll give us the rate of change of my function in that direction. What happens if theta is 0? Or what happens if theta is pi over 2? Take a second and see if you can work out what this thing looks like. Of course, if you do that, the cosines and sines are either 0 or 1, and what you find is those directional derivatives, if you look at the picture, are in the direction of the x-axis or the direction of the y-axis, and those directional derivatives are just the partial derivatives. That's the same limit definition we had for partial derivatives with respect to x and with respect to y. So this makes sense. It's consistent with what we've already got, and it also allows us to find derivatives in other directions that aren't just along the coordinate axes. But limit definitions are typically a pain to work with, so let's see if we can come up with a different way to compute what the excuse me, the directional derivative is without resorting to this limit definition. So let's let x be x naught plus some parameter h times cosine of theta, and y the same, y naught plus that parameter h times sine of theta, like we've seen. Then I can imagine there's a cosine and a sine floating around, but that doesn't change the fact that as h goes down to 0, it's going to do it in a nice way. And so this is just like looking at the change in f as I vary how far along we've moved along the direction of that vector v. And so this is, in a particular sense, the derivative of f. So we got f prime here. But that is exactly how on the previous slide we had just defined the directional derivative in the direction of v. So what that tells us, because really with the definition of x and y that I'm using, what I've got is I can really write f as a function of h, since x naught, y naught are some fixed coordinates of a point, and theta is the fixed angle that we're moving in the direction of. The only parameter there is h. And so I can look at the total derivative. And so what we've talked about with the chain rule for multivariable functions gives me this piece. But I know how x and y are defined. And so that directional derivative is just the partial of f with respect to x times cosine of theta plus the partial of f with respect to y times sine of theta. And that's going to be much nicer to calculate. Remember where that vector v was, cosine theta, sine theta. So I'm taking components of v and partials of f and combining them and getting the exact same thing that we'd get from that limit definition of the directional derivative before. Okay, so let's look at an example. We've got this function which defines some surface, and I've got a particular vector that points in a direction, and I'm interested in how is the height of the surface, how is the function changing as I move in that direction from the point 3, 2. So take a moment and see if you can figure out what the directional derivative is of this function in the direction of this vector at this particular point. And if I didn't make any mistakes, I think you should come up with this value. And so my next question is, that value is negative. What does it mean that that's negative, or what would it mean that that was positive? Well, the picture, here's my surface, and so there's a point on that surface that's above the point in the xy plane 3, 2, and so what this says is if I'm at that point on the surface and I move in the direction of that vector v, that the slope, the height of v is going to be going down, that the slope there is negative. If we were at another point or we were moving in another direction, maybe that'd be positive. But that just tells me how things are changing, how the z values are changing as I move in that particular direction. And so if you look at this picture, that seems pretty believable that we would have a negative slope at that point if we move in that direction. Okay, then just one more thing. So again, here was our definition of the directional derivative in the direction of a vector v. And if we look at this for a minute, we realize that we can write it as a dot product of the vector v with this other vector made up of partial derivatives of f. And we call that vector made up of the partial derivatives of f the gradient of f, and we denote it with this nabla symbol. So that's gradient of f. It's just a vector composed with the partials. If we were in a dimension higher, you'd just have one more partial with respect to z, for instance. And so what it turns out we can write is this, we can write the directional derivative. And so here, the first two pieces there you see are the notations I'd mentioned before for the directional derivative. Now that second one makes a lot more sense because it's related to that gradient. And as it turns out, the directional derivative is just the gradient of the function dotted with the vector in whose direction you're moving. All right, I'll see you guys in class.